DeMorgan's theorem are everybody's favorite theorems. I call them theorem 16 and 17, DeMorgan's theorem. DeMorgan's theorem says that when there's a big inversion bar over a product or a sum, then it's the same as inverting each input separately and switching the sign. So I'm going to put that, write that down here. So if there is, if a product is inverted, here, I'll just write it down for this one. If a product is inverted, it's the same as inverting each input separately and summing them. Now, we don't say product, right? Or sum, because we're not doing multiplication. We're not, or addition. So I'm going to erase this here. Well, I'm going to keep it there, actually, product. And I'm just going to remind you that here, or is inverted. Same as inverting each input separately and ing them. So an illustration of number 16 in a more common way that you usually see it is like this: A and B, if that is completely covered in one large inversion, then that's the same as A or B separately inverted. Okay, now it works the same way like this. Let's say you have apples or oranges, and they are all inverted. That's the same as apples ANDed with oranges. Doesn't matter what it is. Here it was X's and Y's, here it was A's and B's, and here it's apples and oranges. It's a pattern that you're looking for. And you wonder, is that really true? You can do a truth table. Do a truth table for this side. And do a truth table for this side. You tell me if that is true. Should be true. Let's look at number 17. In this case, you have a sum is inverted. That's the same as two products, each inverted. But again, we're not doing sums and products because this isn't regular math. We're doing ORs. And it's an AND combination that's inverted. So here, you're not used to looking at X's and Y's, but that's like saying A and B with a huge inversion across it is the same as A separate from B. Change this sign, invert them separately. So, and that's the same as apples and oranges. All inverted is the same as apples or oranges, separately inverted. So what you've done in DeMorgan's, I'm going to really simplify this, is that both DeMorgan theorems just say, hey, break up the inversion bar and change the sign. That's all there is to it. Break up. That's what DeMorgan's say. Okay, 16 and 17 say break up the inversion bar and change the sign. Again, if you don't believe me, do a truth table for each of them. And the last one is the double inversion law. If you, clearly, if you took A and you inverted it and then you inverted it again, then you would just get A. So let's say let A equal 1. Therefore, A inverted inverted is equal to A is equal to 1 inverted inverted, which equals to 1 inverted is 0 inverted, which equal to 1. And that output is equal to A because I said A equals 1. So that's DeMorgan's theorem and the double inversion law. And now I would like you to rewrite these examples by hand, rewrite them all and work through them and try to see if you can find all of these laws in here. When you're rewriting them, I do recommend that you rewrite them with the inversion over top. So this is the same as A, B bar, D bar. You won't find a DeMorgan's here. Here I'm looking for the common element. I'm factoring D or D bar, but D or D bar, that's the same as, that is the same as saying X or X bar. So one of them is 1, one of them is 0. So therefore the answer must be 1 because if there's a 1 in there, the answer to an OR gate is 1. So this is A, B bar times 1. I mean, and it was 1, which is the same as A, B bar. So write down beside all of yours and write them all by hand and find each theorem that you have used here. And next week will be entirely example problems of just using theorems.